Our next presenter, Julia Greer, is a professor at Caltech, whose key research is the development of three-dimensional nano-architectures and designing experiments to assess their properties and deformation mechanisms. These nano-metamaterials have multiple applications, for example, as biomedical devices, battery electrodes, and lightweight structural materials, and provide a rich playground for fundamental scientific pursuits. Dr. Greer received her bachelor's degree in chemical engineering with a minor in advanced music performance from the MIT and a PhD degree in material science and engineering from Stanford University. The title of her talk is Mechanics and Physics of Nanosolids in Designing 3D Hierarchical Metamaterials. Julia, the floor is yours.
Thank you. Okay, I need to wire up, I think, here. So I actually have a slightly different title here. So it's still just as confusing and it's just as much of a mouthful. So size matters. The importance of all things small. That's really the title that hopefully you'll understand. Or a mouthful title: three-dimensional architectured nanostructured metamaterials. Okay, even if all of you understand each one of these words individually, it's not at all a given that you may understand why they all belong in the same sentence. So hopefully by the end of this talk, I will have conveyed to you why they really do fit together like this. But the most important key message here is that size matters, all right? Okay, so I imagine that many of you have encountered a situation like this. So you walk around, right? I don't know if you're old enough to know this, but you go to the grocery store, you buy a whole bunch of things that you absolutely need, and oh my God, the plastic bag just can't quite hold all the things that you have. And this, of course, goes for a variety of different examples. From that wine glass that never made it to the toast, to the balloons which make our children sad when they pop, and then to the, oh yeah, absolutely meant to have that baby. Yeah. So all of these are examples of materials that are lightweight. Very lightweight, right? Notice they're all lightweight here. But the fact that they're lightweight somehow also makes them be weak, and that is that they're very, very susceptible to damage. All right, let's look at the opposite end of the spectrum. Let's look at the airplanes, right? Materials that are very strong materials that we know how to trust. So we have the Boeing 747, and then I've actually had the pleasure of traveling on a Dreamliner. Maybe some of you have before as well. And the advantage here is that, of course, the body, the skin of the airplane is now made out of a composite material. And so the engineers here were able to reduce the weight of their airplane from about 1 million pounds down to about half of that weight, about 500,000 pounds. And now these airplanes use about 20% less fuel, which results in a tremendous savings in terms of the money. So it turns out that the largest constituent of the cost in the airline industry comes from propelling a million pound machine through the air. That's how much fuel it's going to require. So these are the airplane examples, right? So these materials are strong, but also they are heavy and also expensive, right? So let's look at a different example. Another example here, we're all in California. You've probably seen this kind of a situation before. This is an installation of a solar panel. These are generally made out of single crystalline silicon, which is a very brittle material. So for this particular application, it's highly specialized. So again, we have these materials that are heavy and also brittle. What happens if this poor guy slips off accidentally? This is going to be really bad news, so this material will break, right? And this is, again, this is going to be expensive, and it's all about the materials. So it turns out the materials are really a problem here. So in whatever happened to that space elevator? Maybe some of you remember how about a decade ago, maybe a little less than that, we were all so excited about building this elevator to go up into space. And why haven't we built one yet? Why isn't there one? Well, it turns out that this is the answer. The answer is this. There is this tremendous coupling between the material strength and the material density. And I chose to plot the strength here, but it doesn't have to be strength. It can be any other mechanical attribute. It could be fracture toughness. It could be stiffness. But the point is that materials that are very, very strong are also very, very heavy. So this is a log-log plot. What that means here is that even a small increment within the space represents a substantial difference, and that the straight line actually represents a power law. Right? This is a logarithm. So what that tells you is that everything that we already know how to make today, these are all the materials that are available to us, is already plotted here. right? So materials can be either strong and heavy or lightweight and weak. And this is why we have all these challenges and all these problems that I just outlined in my previous slide. So wouldn't it be great if somehow we could learn how to make materials that were both very, very lightweight and at the same time very, very strong? We can't go above the theoretical maximum. This is, of course, all materials have an intrinsic strength at which the atomic bonds break. But this space, like I said, this is a log-log plot. This space is quite prominent, and it's really important to figure out how to make materials in this region, right? Because this is where we're going to be able to make vacuum balloons, for example, instead of filling them up with helium. So how do we do that? If everything that we already know how to make today is already plotted here, do you have any ideas? Anybody ideas? All right, well, this is at least how we think of it. We utilize the concept of architecture in material design. And the analogy I'd like to draw here is this. This is the Great Pyramid of Giza. This is the largest man-made stone monument. Maybe some of you have seen it in real life. It's unbelievably heavy. Okay, it's huge. So you can look at the original height is about 150 meters. It's pretty tall. It weighs nearly 6 million tons. And the weight at the base, if you look right here, this is a very wide base, right, is about 10,000 tons per meter squared. This is measured in tons. All right? And let's contrast this, compare this to the Eiffel Tower. It's a very elegant structure. Again, hopefully maybe even more of you have seen this in real life. Its height is about 320 meters, so it's about twice as tall. It weighs 3 orders of magnitude less, and its force on the foundation is next to nothing compared to this guy. And you can see that it contains mainly of air. Right? This is an engineered structure. So we use the same type of a concept of architecture in designing our materials. So this is a real image. This is a microlattice that was made by our collaborators at HRL, Hughes Research Lab in Malibu, which is nearby here. And actually, one of our collaborators is here. You see Irvine. These microlattices contain entirely of nickel. They're made out of entirely of nickel. They're about 99% air. And this is the world's absolutely normal dandelion. There's nothing photoshopped in this picture. This is not the world's strongest dandelion. This is a normal dandelion, and this is one of these microlattices that's sitting on top of it, and you can see it's hardly perturbing it at all. This is a very, very lightweight structure. So this is a microlattice. In fact, if I were to hold one of these microlattices in one hand and a feather in the other, and then release them from the same height, the feather would fall faster. They're very, very lightweight. Okay, but they're made out of nickel, right? Nickel is not a lightweight material. Nickel is a metal, right? Okay, so this is one example of how structures or very small structures can be engineered to be very, very lightweight. But I promised you something even beyond that, something that's very lightweight. That's not, well, it's kind of cool, but that's not everything that we need. We need them to be strong too. And to get to the lightweight and strong, we have to go down. We have to go down to the nanometer size. And so these are the nanolattices that we make in our lab. These are computer-generated images of what the unit cell looks like. And these are the real images. So even though they're black and white, they're actual micrographs. They're taken with a scanning electron microscope or an SEM, which show you what they look like in real life. Now, if you look at this structure, your eye can discern all the structural elements in it very easily. If you look at this one with your naked eye, it just looks like a cloud. So it's just like you're holding a cloud that's sitting on your hand, but unlike the aerogel, it won't crumple if you rub it between your fingers. So these are very small. And you can see some more examples of the structures that we made in our lab. I don't know if any of you are Doctor Who characters, but this is the TARDIS, Doctor Who fans, but this is the TARDIS that we made in our lab that's about the size of about 1/10,000th of your hair diameter. Okay? Now, all of these structures, little elements in here, they're 100,000th of your hair diameter. These are very small structures. Okay? But they're real. They're real. These are not computer generated. These are actual pictures. You can see that we're not limited to periodicity. We can make these architectures in a variety of different ways. So even though some of these lattices are periodic, this one certainly isn't. This is a truncated dodecahedron. Took me a while to learn how to pronounce this word. That's made out of a biocompatible material, biodegradable material that you can put into your body and it won't contaminate it. This is a so-called Kagome lattice. This is an interesting lattice because when you look at it from above, it looks like a tessellated network of triangles in a hexagonal pattern, like Stars of David, for example, that are used in butterfly wings, for example. If you look at a butterfly wing, this is what they look like, but in 2 dimensions. These are the ones that we made in 3 dimensions. Now, these different architectures contain 99.9% air. And the reason why is because they're highly, highly porous. So if you look at the individual unit cells here, they're all open. This is all air. But on top of that, there's a second level of openness here. And that is that the tubes that comprise them are hollow. And look at the wall thickness here. The wall thickness here is on the order of 10 nanometers. That's 1/100,000th of your hair diameter. 10 nanometers. This is very, very small. Okay, and individual tube widths are about 500 nanometers. Then you go to their lengths, and they may be some microns. Then you go to the unit cells, maybe hundreds of microns, and the entire material eventually will be in the centimeter length scale. So this single material embodies every length scale, from nanometers to some microns to hundreds of microns, and even to the macro scale at some point. So this is why we call these metamaterials, because their deformation, their properties are no longer independently driven either by their structure, like the Eiffel Tower, or by the material, like it's a metal versus a ceramic, but the combination of the two. And when you look at these very small sizes, when you look at the combination of the two, they're no longer independent from one another. And this is what tipped us off to start making these, and I'll show you some of the interesting properties that they have. This particular image I really like because it's a fractal nanotruss. Notice how the individual beams here are no longer just hollow tubes, but they're now made out of the self-similar fractal-like pattern. Do you see this? So that and they don't have to be self-similar, but this is how we learn how to build hierarchy into these materials. Now, and like I said, the reason why we call it a metamaterial is because the properties are no longer independently controlled. So it's not like just scaling down the Eiffel Tower. It's actually looking at the material properties at each relevant length scale. Now, to tell you something, so I told you that they can be strong, but so far I haven't really explained how. Well, this is what I mean by the size effect in the nanomaterials. So it turns out when you reduce the dimensions of materials to the nanometer level, they exhibit different properties, especially in the mechanical world. So if we were to plot some kind of strength, this is a strength, as a function of the external size, and again, this is a log-log plot, what you will see is that many metals that we're familiar with, for example, gold or nickel or copper, become stronger when they get smaller. What that means is that if you take your earring, which is made out of gold, it's very malleable, right? We've all held malleable metals before. And you reduce its dimensions to about 200 nanometers, it becomes as strong as steel. Okay? But there's something special about the atomic arrangements in these gold. They're called single crystals in these particular metals. So this is what we call a smaller is stronger size effect. Now take exactly the same metal and deposit it somehow differently, right? There are different ways to deposit nickel, different ways to deposit gold. And now you're going to see exactly the opposite trend. Smaller becomes weaker. Okay? So there's something about the atomic arrangements within these metals that can be changed by the deposition technique. They can provide you with a tuning knob, effectively, to control their strength. So sometimes materials get stronger, and sometimes they can be weaker. But all of these effects you can only see at the nanoscale. You can see the scale here is in the nanometer range. Now, the size effects don't have to manifest themselves in strength only. In fact, when you look at something brittle, and the example I'm showing you here are called metallic glasses. They're effectively glasses. So we all know the glass will shatter, right? That are made out entirely of metals. So when you look at something that's large, and for us large is half a micron, still pretty small, and you look at their stress-strain curve, you guys may not know. Does everybody here know what stresses and strains are? Do you know what forces are? All right, so when you pull on something, you apply a force, and somehow that's related to to stress. And when you displace something in response to that force, that's called strain. See, I actually am supposed to teach a class today, so here I am teaching a class. So it's very common to measure a curve in engineering that represents that measures a force as a function of displacement, for example, right? How hard you have to pull something for it to displace by a certain amount. So this is what a stress-strain curve looks like, and you can see all of these are pretty catastrophic. So you basically pull on it and then it breaks. You pull on it and then it breaks, and these are the breaking lines. These are something that we call shear bands. So a glass shatters at the large sizes, right? If you take a piece of glass, I'm sure the wine glass that I showed you before. But when you reduce the dimensions of this glass to about 100 nanometers, you can pull on it and it forms a neck, just like you would observe in a typical metal. And actually, it stops breaking. And all of this is the non-breaking. That's how much it can suppress failure. So instead of just being loaded and then shattering, it's being loaded and then extending. And we didn't change anything about this material other than its size. So Another example of a brittle material, smaller becomes tougher. And tougher means that it's more resilient. It suppresses breaking effectively. So what I'm trying to show you in this, oh yeah, here we go. So it's actually a movie. So watch this. We're pushing on this ceramic nanolattice, which is very, very brittle, and it's bending. When you take a piece of chalk and you try to bend it, is it going to bend? No. Pieces of chalk don't bend. They do what instead? They break, right? This is effectively a nano piece of chalk, and instead of breaking, it's bending, it's deforming by a tremendous amount over multiple cycles without breaking at all. So this is what happens at the nanoscale. So the message here is this. Sometimes materials can get stronger. Sometimes they get weaker. And other times they stop breaking. All of these effects are lucrative, but they emerge only at the nanoscale. So somehow what we needed to figure out is how to harness and to capture these nano size effects into a larger structure. So this is where this combination of the material size effect and the architecture comes into play. It's effectively, what we're doing is we're wrapping a two-dimensional nano ribbon around a three-dimensional architecture. And we're hoping to elicit the same response. We're hoping to harness all of these properties from this nano ribbon, because that's going to be the largest solid dimension in your entire nano lattice structure, and then hope that we can harness these properties. All right, so let's see if we succeeded at doing this. So what I'm about to show you is a movie. Now, this is an octet nanolattice. This is made out entirely of alumina. Does anybody know what alumina is? It's a what? Alumina, not a metal. Alumina is alumina. It has aluminum in it, but it's aluminum oxide actually. And it's effectively, it's very much like a piece of chalk. It's what your coffee mug is made out of. So it's a ceramic. It's a very typical, common ceramic. What do we know about ceramics? What happens if you throw your coffee mug on the floor? Especially the China ones. They're really fine. They're going to break and shatter. Absolutely, right? But now imagine we're going to make this case even worse. We're going to give it osteoporosis. All right? So it's going to be your fine china cup that's very, very thin-walled with a whole lot of holes in it, so much so that it's 99% air. So put a lot of holes in it. Okay? Now, the wall thickness in these is 50 nanometers. So this is an octet nanolattice. The wall thickness is 50 nanometers, right? And it's full of holes. And so what we're going to do now this is an actual movie inside of an actual electron microscope that we're going to compress right now, right? So what should happen? It should shatter, right? Absolutely shatter. All right, so let's see if that's what happens. So here we are. We're compressing this thing. Bam! It totally shatters. It's crumpled. It's gone, just like you predicted. Thank you very much. I'm just going to go home now. No. So, right. So it's shattered just like you predicted. But this is a little bit disappointing, right? There's one aspect that's not so disappointing. Its strength is still measured in something that we're calling megapascals, which is very strong. So despite it being very, very thin, it's effectively like toilet paper, made out of toilet paper. That's all ceramic. But it's still very, very strong despite having such a low density. So what we learned about these, and we're calling these thick-walled nanotrusses, is that they're strong, but they're still brittle. So there might be something interesting there, but we're not quite there yet. So here's what we did, and this is the work of my student Lucas. So here's what Lucas did. He said, all right, well, maybe we just didn't get small enough. So here's what we're going to do. We're going to do exactly the same experiment. We're going to repeat this experiment on exactly the same architecture, exactly the same geometry, the same everything, except we're going to change the wall thickness to 10 nanometers. So we're going to reduce it by a factor of 5. Okay? So instead of 50 nanometers, we're going to now look at the same everything with a wall thickness of 10 nanometers, right? And now, so it should crumple even more, right? We made it even thinner. We went from pieces of paper to toilet paper, right? So it should crumple even more. So let's see what happens here. The ceramic. This is your cup, coffee cup. 99% air ceramic. Look at this. Look what it's doing. It's not shattering at all. It's not shattering, but look even more. It recovers. So Lucas just made a ceramic that's 99% air. That's really strong. That recovers. That doesn't shatter at all. So if that doesn't show you, if that doesn't demonstrate to you that there is, in fact, a real material size effect, I might as well just really go home now. So this is a manifestation. And all we did was reduce the wall thickness, right? So this shows you right away that there's so much unknown phenomena down at the bottom, like Richard Feynman said, which needs to be explored. So now, would you like to know why this happened? Who wants to know why this happened? Yes, awesome, good, the inquisitive mind. All right, well, I'll tell you. So this is a bunch of formulas here. This is mechanics. How many of you have seen these formulas before? Everybody who's not in mechanics. Okay, all right. So if you look at the unit cell, you can actually model, so again, this concept of stresses. So a stress is effectively an intensity of force at a particular location. All right, so stress is a measure of force, but divided by that area, basically the intensity, force intensity. So materials can fail by two different ways. They can yield, which means that after the elastic deformation, they can go transition into plastic deformation, or they can buckle. And what I mean by buckling is if you take an empty soda can and step on it, it'll buckle. Right? You've probably seen buckling before. Now, this is a very brittle material. Right? I told you this is a ceramic. So when we say yielding, it doesn't really yield. So after the elastic deformation, it just snaps like a piece of chalk. So this material will either break or buckle. And it turns out, there's a critical ratio between the wall thickness, that's what the T is, and the diameter of the tube, that if you're above that ratio, your material will break, and if you're below that ratio, the material will buckle. And if it buckles, it'll recover. Right? So you can imagine buckling, like take a tall eraser, and then just press on it, right? So it'll buckle, bow out, and go back. That's called buckling. Now, all right, so let's see if that holds, okay? So these are our very, very thin nanotrusses. The TO ray here is 0.016, so that's below 0.03. And you can see this is the image after. You would never know that this image was taken after the deformation because it looks exactly the same as before. And if you look, this is the deformation curve. You see we've deformed it to about 50%. So we squashed it to about half of its height, and then it fully recovered. And these are different unit cell sizes. So they all recover. And now let's see what happens when you increase the wall thickness. So going just a little bit above to 20 nanometers, it's really trying to recover, and it kind of did it almost all the way, but not quite. This guy really tried and didn't quite succeed, and this guy's just a goner. Right? See, this is the movie that I showed you before. So you can see that as we deviate farther and farther from this critical ratio, your materials become really brittle. They go back to the behavior that they originally had. Right? And you really had to get down to these very, very small scales to elicit this new behavior where they recover. Right? And also look at the signature. So this is something we call data, right? This is the data that we actually collected. You can see that here it's relatively continuous and relatively smooth. There might be some bumps in there, some undulations, but here this is very discrete. Right? It's just loading a single burst, and then there's no recovery, and it just unloads. Right? So everything is changing. So there's a lot of things that are changing. But here's the more inquisitive ones of you might be wondering, well, wait a minute, you told us that there's something about the size effect, but now you're telling us it's all about this ratio, T over A. Well, T over A is scale-free. So what would happen if we were to blow this thing up in a self-similar way to being 2 kilometers by 2 kilometers by 2 kilometers, where the wall thickness is 10 centimeters, and the diameter would have to be 3 meters then, or the radius would have to be 3 meters then? Would you ever see the same behavior? Can you imagine these gray concrete tubes, an interwoven network of these gray giant concrete tubes, and then we push on them and then they recover? Would that ever happen? But why? Our mechanics theory says that it should, as long as your ratio is maintained. Why would that never happen? You're right, it wouldn't. How does the size effect manifest itself here? It's too big, sure. But our theory says it's all about the ratio. There's nothing too big. The TO ray is the same. Right? So 10 centimeters divided by 3 meters is the same thing as 10 nanometers divided by 300 nanometers. Right? Any ideas? From the students mainly? Actually, even from the wiser people? Yeah?
Because the material behaves differently when it's such a small scale, so it interacts differently with itself.
You're sort of on the right track. Right. So does everybody see the paradox here? Does everybody see that if we're saying that the whole thing can be explained by this theory that's based entirely on the ratio, but that means that it should hold at every scale because the ratios are scale-free. So this is the answer. At the large scale, all brittle materials fail at flaws. Every brittle material, like a ceramic, like a brick, like a concrete, anything, contains tiny little pores, contains slightly larger pores, contains defects. And these defects, we're calling them flaws. And necessarily, your material will break at a flaw. If you drop a piece of brick down, it will shatter, initiating at these little pores and voids and flaws, right? The probability of finding a flaw, a whole bunch of flaws, in something that's 10 centimeters thick is 100%. The probability of finding a relatively weak flaw is also 100%, which means that when you start pushing on it, your material will always break before anything else. It'll just break. In these structures, first of all, the size of the largest flaw is only 10 nanometers. So these are tiny, tiny, tiny flaws. And secondly, the probability of finding one in something that's that thin is much, much lower. So when you start pushing on it, your material is able to buckle and to undergo other deformation modes before failing, before fracture. So do you see this? We're able to, these materials are so close to being ideal, to being defect-free, that they're able to exhibit other deformation modes before breaking. So that's how the size effect manifests itself here. So in the last 3 minutes that I have, I just want to show you, I told you we were going to hit the white space, right? Or we were hoping to. So let's see how we did. So these are purple. The purple points and the orange points are here are all our data. So this is what I showed you before, what everybody already knows how to make. And this is where we are. And again, in the log space, you can already see that we're not quite where we need to be, but we're on our way. So you can see that all of these data points are already very much pushing the envelope here. And for example, we've made some of the most lightweight, structurally robust materials that people have never made before. So this was really exciting to us. Maybe this really works. Combining the architecture and the size effect, maybe this really, really works. So what that tells us is that we now have all the necessary tuning knobs to make entirely new classes of materials, to make materials that people have never made of before, even thought of before possibly, and to create entirely new design criteria. And what I mean by this, I'm going to skip through this. This is how we measure them. But I wanted to show you what I mean by this is this. We can make materials which when you push on them, only the bottom part is deforming, but the top part doesn't even know that it's being pushed on. So these are new materials. These are all, this is made out of gold, actually, and this is the data that you're collecting, that we are able to collect at the same time. You can look at this one. So this is a pyramid that's got the fractal beams. So for example, a lot of biological materials have this built-in hierarchy into their structure. So what does hierarchy buy you? So again, this is a brittle ceramic, okay, and let's see what happens to this one. So we're pushing on this pyramid. So the first thing that happens is that the pointy top gets compressed, and then we keep on compressing it, and look what happens to its beam members, and oh, this guy is not happy. Oh, it's really bringing him down to its knees. This is kind of almost hurts when it's doing this, right? It's pushing it a lot. Bam, doesn't even know it was being compressed. Right? So this is your ceramic. This is what materials shouldn't do. Okay, I'm showing you everything so when you go to take your classes in college, you're going to say to the professors that everything that they're teaching you is not quite right at the nanoscale. Right. We can also pull on these things. So this is a tensile experiment. So you can see this is my student Lauren was doing this, and she just ripped off its head. So we can do pushing and pulling and also bending. Yes, they're real. We make them. We have a special instrument that allows us to write structures into a polymer. And after we've written a structure into a polymer, we coat it with the material that we're ultimately interested in, and then we get rid of the polymer. So it's effectively like a chocolate bunny for Easter. You know those hollow candy that you have? There's nothing on the inside. So I showed you that they're hollow, and so this is how we make them to be hollow, because everything we write in the beginning is a sacrificial scaffold that we can get rid of after we've wrapped that nano ribbon all around it. And just to finish up, so you might be looking at them and thinking, yeah, okay, these are cute, but what are they good for? So these are some of the examples of the real technological applications that these might be useful for. For example, in energy storage, there's a tremendous push now for sustainability, right? So how do we store all that energy? Well, there are a lot of batteries, for example. There are a lot of different battery technologies, lithium air, lithium ion, perhaps you've heard of these. So there's a tremendous push to start using silicon instead of carbon on the anode side because it can absorb an order of magnitude more lithium. Well, what happens to silicon or anything brittle when you try to shove 300% of lithium into it? It tries to expand, but it can't, and so it cracks. And you don't want your battery to do this. There's a lot of unsafe chemistry that happens there. Well, it turns out that if you can go to the nano level and then to architect them into these intricate structures, maybe you really can. So this is a movie that my student Xiao Sheng made. You can see, look at this expanding. So he's lithiating these structures. They're made out of silicon. And then he delithiates them. So you can see it's getting skinnier as the lithium is traveling out of it. So you can really bypass failure. You can really make, for example, much safer and more efficient batteries. Another pursuit that we're after is three-dimensional scaffolds for cell growth. These are real cells. These are your bone cells. So we can possibly start writing the bone in our own lab. So for example, if you make this scaffold out of the appropriate biocompatible material, and I showed you that you can make them out of any material that you want, these are the real cells that have some affinity for these nanotrusses, and they can start generating the bone on their own. Now, I work at Caltech, and possibly you've heard of Richard Feynman and some other famous people who also happen to work at Caltech. Now, at Caltech, you can only major in physics. You can major in physics with a material science flavor. You can major in physics with a biology flavor. You can major in physics with even a humanities flavor I hear, but it's really all physics. So I have to show you an example from applied physics. So these are so-called photonic crystals. So these are periodic lattices, and that means that when you make them small enough, they can couple into light, and they can interact with the light in such a way that you can entice a photonic band gap, or have a certain frequency or in a wavelength at which all the light that travels into the structure gets trapped inside, so nothing is lost on the outside. And so my student Vicky demonstrated that not only is there a photonic band gap, but it shifts as a function of strain or how far you squash it. So when you squash it, it shifts the photonic band gap, so you can make these optical switches. So for example, your light can modulate between red and blue very, very efficiently. And right, and then this is the last example that I want to share with you. So this is probably the example that I'm particularly excited about because it's biomimicking. So the reason why we even started working on these is they're inspired by biology. So look at this tiny little structure. This is a radiolarian. It's a little tiny diatom that you can't really see with your eyes. They are all over, they exist in the ocean. So this is made out entirely of silica, like a piece of sand. And if you look at all of these holes at the top, they're extremely well arranged. So it's like a tambourine with two different platelets, one on top and one on the bottom, and each platelet is made out of these hexagonal shaped cookie cutters on the inside, and they're all empty chambers. So cookie cutters all aligned right next to each other, one platelet, bottom plate, top platelet, bottom platelet, and then there's a belt that goes around them. Why the heck would nature make these like that? Why? It's a live organism, and it's not clear why. Now, you know that these live in the ocean, of course, right? So they're subjected to extreme thermomechanical environments with the sand and the wave and the temperature fluctuations, and they are extremely resilient, so they survive. And there's something about the hierarchical design, there's something about the constructs of their materials that comprise them that enables them to be so resilient. So what we can do in our lab already is to study the models. This biological system is too complex because nature has had millions of years of evolution to get to that structure. We don't have millions of years. I don't have enough grad student life years to do that. So we have to do the forward problem where we create the model systems and then we study them and then we understand their effects instead of trying to reverse engineer. So here's a question for you. One of these things is not like the others. So one of these things, or maybe none of these things, are real biological structures, and some of them were made in our lab. Do you have any ideas for which ones might be which? Yeah.
The one on the far right, you mentioned earlier that I think it's...
Yeah, you're right. Okay, so we made this one. I'm kind of hoping that you would be wrong, but yeah, you're right. Okay, so this one we made. Any other guesses? It's too complex. Yeah, okay. What about these guys? They may all be, we're done with time. Okay, this is my last example. So hopefully some of you are at least a little bit confused. Maybe some of you are like, whatever, I know which one. Right? But hopefully you're at least thinking about it. So this is the real biological structure, the middle one, and then both of these were made in our lab. So what that tells you is that we're able to make materials that are on the same scale, made out of exactly the same materials as the nature makes them, and then to study their properties. So with that, I'd like to finish and to show you, hopefully I have now demonstrated to you that if you have three ingredients, one of them is the architecture, The second one is nanomaterials. And the third one is atomic arrangements. You can really create anything you want. You can make materials that are so that the world that all of these guys grow up in. So these are all, maybe you have younger siblings. So these are all, some of these happen to be my children. But some of these children would grow up in the world where there are no hearing aids, because we'll just be able to just write the bone, the little bone that you have in your ear, and then you won't need to rely on these. In the world where the iPhone 83, the battery of the iPhone 83 is going to last for years, in the world where the balloons won't have to be filled up with helium because they're going to be strong enough where you can just suck the air out and make them be vacuum balloons, where the Christmas ornaments, of course, will never break. And here's my favorite example, brownies. We're going to make chocolate nanotresses, which are 100% taste, 99.9% air, and 0.01% calories. Thank you. So I have some time for questions, right?
I was wondering, could you make these nanotresses, like, because you showed like the Dalek and you said it was really, really, really tiny. Could you make like a life-size structure but with still these tiny, tiny tresses and still have it be just as resilient?
Yeah, that's a terrific question. The question was about scalability. Can you scale these up to have larger dimensions? That's something that we're working on right now. And that technique that we're using right at this moment is not so amenable to scaling up because it's very long. It would just take too long. But in this process, complexity comes for free. So you wouldn't want to make very large structures of it. What you would want to do is to make complex, small structures, but a large number of them. So for us, the scale up is not so much in making large sheets of it. Of course, we can make on tearable paper. So if we were to roll print them, for example, which is what we're trying, we have a plan. We're trying to work this out with, we have a partnership actually with a few other institutions. You can make tear-proof paper. You can make anything that doesn't tear effectively, right? We won't be able to hold the liquid inside to make the coffee cups, because they're 99% air. But yeah, no, there are many applications, and the ones that I showed that would require, instead of a large amount of material, would require a large number of small components, so that's what we're focusing on. And right now, for example, one possibility would be to develop a holographic type of an approach where you can create a standing array. So instead of using one laser to write it, we can have an array of lasers and create a standing pattern of dots, for example, and then maybe go somewhere with that. So that's what we're pursuing. Excellent question.
In your opinion, for a student who wants to pursue a career in nano research, would it be more effective to go into physics or like chemical engineering or mechanical engineering, or what do you think would be the best approach to that?
All of the above. Just major in a real discipline. Don't major in material science for your undergrad. Yeah, I'm absolutely serious. So for your undergraduate degree, pick something real. So all the ones that you mentioned, mechanical engineering, chemical engineering, physics, they're all terrific. I would save the designer, so to speak, majors like material science or controlling dynamic systems or robotics or something like that for graduate school. Because what everybody looks for in nano research is kind of like a designer branch, I would say, within material science, but it's also very, very interdisciplinary. So what we look for is the real solid backgrounds, and then so that will enable you to have the tools, the necessary tools to pursue that kind of research. Yeah.
And how do you measure the strain, the deformation of a nanoscale material? I know what a strain gauge is, but how do you measure the deformation at the nanoscale?
All right. So the question was, how do we measure the stresses and strains? So there's an instrument that's called a nanoindenter. So it's a commercially available instrument. And so what we did is we used the nanoindenter type of an instrument, and we inserted it into a scanning electron microscope. So all the movies that I showed you, also, I don't know if you know, maybe some of you noticed, also had data with it. So the nanoindenter part, it's an electromagnetic assembly which applies the voltage, which then translates into force. So you apply a force and you measure the displacement by the leaf springs of the capacitor that's within it, very much like a nanoindenter does. But what we did, the innovation that we did, is we put it inside of an SEM so we can see what we're doing. So we can, for example, doing compression is really easy, right? On a nanostructure, you can do it like this, and eventually you'll hit it, and then you can measure it like in the nanoindenter. But tension is impossible, right? Because you have to grab it. So you have to see what you're doing, and then, just like you pointed out, on a nanostructure, you can't see what you're doing, right? So you have to have something like this. I'm sorry for bringing water inside this auditorium. You have to have this, And then you have to be able to see what you're grabbing and then being able to grip it. And after that, so then we make our own grips, and then we attach them to the nanoindentor-like module, and then that's what enables us to measure it. Yes. Oh, a woman. Yes. Finally.
Hello. Love your shirt. Love your research, by the way.
Thank you.
But my question was, what made you interested in this research, basically? Like, what inspired you to take on this research and this challenge, essentially?
This particular nanotrust one, or research in general?
Both, if you can.
Okay, so I actually have sort of an interesting, I guess, answer to this, but that's a very broad question. I had to choose between music and math when I was 14. So I grew up in Moscow, and that's where you have to. So, and I did piano. I don't know if you got the message. I'm also a pianist. So we had to choose when we were 14, and so this is where I heard the advice from my piano teacher, who said, if there's anything else you're good at that would also pay money, go to that. Because you can always do music on the side, and it turned out to be right. So, because you can't quite do science on the side. So I had to pick math really early on. And then when I went to college, I didn't really, I think a lot of you will experience this. When you go to college, everything is exciting, and there's such an information overload that you just and you do your thing, and you have your micro environment, and, you hang out with your friends, and so you have your life. Your life pretty much belongs to that college, I guess, or school that you're going to be in. And you're not really thinking so much about what kind of research do I want to do, but rather, these are all really cool things around me. How can I get into them? Right? And so a lot of it is luck. But you have to be really driven. You have to really want to do something. And whatever the topic that you are going to pursue is sort of, I would even say, is of secondary importance. Go seek opportunities out. So I had 10 high school students that worked in my group last summer, and a whole, even more undergraduate students who worked just in our group alone. I will never do that again, because my graduate students cried. But the point is that there are many, many university labs and industrial labs that are amenable to high school students and to undergraduate students coming and doing research. And I would almost say, just get your hands wet. Like, go do research somewhere, right? And then the topic just happened to be, so the topic that I happened to be lucky to do in my graduate school was on these nanopillars. So they were individual nanopillars that were extremely phallic looking. And we figured out how to deform them, and we discovered actually this little smaller, stronger size effect that I showed you was something that we discovered in my PhD. And I worked with Professor Bill Nix, who is actually a member of all 3 national academies and just is an amazing, amazing mentor, an amazing guy. And I happened to be lucky that we discovered this, and in the back of my mind, I always had this question, well, these are individual nanopillars. There's not much, you can't build a plane out of them, right? So I've always had this vision, what would happen if we used them as nano Legos and constructed something out of them to make a bigger material? So this is where this concept was born, I think, and maybe it was even maybe about 10 years ago that I started thinking about this. And then it was a process. It was an evolution process, and then I met up with these guys from HRL, and we made the microlattices, and then I said, maybe this is my chance. Maybe this is where we're really going to be able to construct these nanopillars into a much more intricate, complex network, and sure enough, it worked. We captured the size effect, so that was a big winning moment. But yeah, it's a process. Just I would say don't limit yourself. Just go do some cool research, and it'll be awesome no matter what.
Thank you.
Oh, thank you. Is that it? That's true. Yeah.
Well, Julia, thank you very much for a most exciting, obviously most engaging talk.
Thank you.
I think you're probably going to have your emails are going to be filled with requests for summer opportunities now. Prepare your graduate students accordingly. We have basically a honor document for the Gilbreth Lecturership. It says, to Julia R. Greer, hereby honored as a recipient of the Gilbreth Lecturership in recognition of outstanding contributions to the field of nanotechnology and presentation of her lecture on designing 3D hierarchical medical materials at the National Academy of Engineering 2015 National Meeting. Julia, thank you very, very much.
Thank you so much.
Thank you very much. Probably over here.